Welcome to Brain Vision.
Okay, this is question 5.114, double Atwood's machine. So we have the system of two pulleys and three different masses attached here. So we are asked in part A to find the acceleration of block M3. So we have a lot of different variables here, a lot of different systems. So our strategy here is just going to be to try and write down as many equations as we can, and then try to get enough so that we can solve them and eventually end up with M3. So let's start by considering the Newton's second law equations for each of these blocks. So since this system, the acceleration in all of these cases is going to be down because everything is going to be falling down because gravity is the only real force acting on it other than the tension that's going to be holding up each of these weights. So I'm going to call down the negative y direction to be the actual positive direction here, just to make things easier. So if we look at block M1 here, we have the gravitational force, so the weight of this block, pulling it down. So that's going to be M1 times G. And then opposing that, pulling up, is going to be the tension in rope A. So I'm going to label that TA to refer to the tension in A. And that's going to be equal to M1 times A1. Here I'm going to just label A1 is the acceleration of block 1, A2 is the acceleration of block 2, and so on. We can do the same thing for the other two blocks. So block M2, this is also connected to wire A, so it's going to be the same. We'll have M2G pulling it down, and then TA again is the tension pulling up. And that's going to be equal to M2 times A2. And then for block 3 is connected to rope C. So we're going to have M3G minus TC, and that's equal to M3 times A3. So we have three equations here, but we don't know TC or TA or any of the accelerations. So we need some more equations here to solve. So let's think about, for example, this pulley B. We know that there can't be any net force on it because we are told that we know that these forces are going to have to balance out. So we know that TC here is going to have to be equal to 2 times both these tension forces pulling this. If one of these tension forces was different, then we would end up with a twisting rotation. This pulley wouldn't be stable. So we know that TC has to be equal to 2 times TA. So that'll help give us one more variable. And then we need one more equation. So one thing that we can notice is that if the acceleration of pulley B here, let's call that AB, that's going to have to be equal to minus A of mass 3, because these are both connected to the same pulley. So if one goes up, the other's going to have to go down, and vice versa. And now the acceleration of B is just going to be the average of the accelerations of 1 and 2. So AB is going to be A1 plus A2 divided by 2. So this will give us, if we multiply both sides by 2, will give us minus 2 times A3. Okay, so now we have 5 equations, and we have 5 unknown variables, TA, TC, A1, A2, and A3. So we can solve these. Won't be easy, but in theory we have 5 equations and 5 unknowns, so we can solve this. So let's use, why don't we use this equation first and plug in. We'll use our A1 and A2 here to find, let's solve each of these for A1 and A2. So I'm going to divide both sides by M1 here. There are a lot of different ways that we could solve this system of equations, so I'm just going to show one example, but there would be other approaches to do this. So here we end up with A1 and A2. So once we have this, we can substitute that into this equation here. So I'm going to plug in this A1 here for this, and I'm going to plug in our A2 here for this. So now this is going to give us A3 in terms of TA. So we can get A3 if we divide both sides. Well, first of all, we can consolidate. We have 2G over here, and then we have minus this minus this. We can now we need to divide by this -2, so that's going to turn this into a minus. This will become a plus. We'll have over 2 m1, and this will be turned into a plus and divided by 2 m2. And we can pull out this factor of TA from both of these terms. So just to explicitly show, so we have this in terms of just TA here, which we still don't know. But then we can use our third equation over here combined with this one. So let's gonna bring these two down. So if we plug in TC is 2TA, I'm going to plug that into this equation here. Then we can plug this in. We can solve this equation for TA to plug in to this equation up here. So I'm going to subtract this on both sides, and then I'm going to add 2TA over here. And now finally, if I divide both sides by 2, we'll get TA. So let's write this on this side. So TA is here. So we can plug in our expression, this here for TA in this, and that's going to give us, we'll have this over here. This is now going to give us this divided by 2 over here. So now we have A3 in terms of only A3 and then M1 and M2 and M3. So we need to combine terms, move this A3 to the other side, and rearrange this equation. And I'm not going to actually go through and do all of that algebra here, but you can do it, and you'll find that A3 is going to be equal to G times, this is all the numerator here. We have 4 M1 M2 plus M2 M3 plus M1 M3. And then the denominator will be the same thing, except this term, first term, is positive. So we should end up with this pretty messy, but it's all in terms of M1, M2, and M3 and G. So this is going to be our answer for part A. Now, part B asks us for the acceleration of pulley B. So did we, all right, so I guess I didn't keep the equation, but if you remember, we were talking about the acceleration of pulley B and its connection to mass 3. So if mass 3 is accelerating down with some magnitude, mass B is going to have to be accelerating up with the same magnitude. So the acceleration for pulley B is going to be the same as A3. It's just going to be in the opposite direction. Now part C asks us for the acceleration of block M1. So this is, again, going to require some algebra, but luckily we've already done a little bit of the work. So we can use, let's see which equation will be the easiest ones to use. Probably this one here. So I'm going to copy these over onto a new slide over here so we can kind of start new here. All right, so I'm going to use this equation A1, we're trying to, remember, find our equation. We want to find A1. So, and we have A3, so I'm going to keep this here because this is something that we already know. So if we use our equation A1 here, we can plug in for TA because we found this down here. So I'm going to plug that in. This factor of 2 now comes down here. So now I've just plugged in to this equation. And so now we have this in terms of M3 and A3 and M1. So that's perfect because now we already have A3 in terms of everything that we want. So to solve for A1 here, what we're going to want to do is plug in A3 into this equation and then simplify it. So that's going to be pretty messy. I'm, again, not going to do out all of the algebra, but we should find that it simplifies out pretty well. It's going to look pretty similar to the expression for A1, except we have this. Instead of just plus 1 here, we're going to end up with a minus 3 times M2, M3, and then M1, M3 here. And then everything else is going to be the same. So again, messy, but we end up with our answer here. Now, part D asks for the acceleration of block M2. So guess what we're going to end up doing? We're going to do the exact same thing as before, except now we're using this equation, plugging in the same equation that we got before, our TA. So we had this, just doing the exact same thing. And if you notice here, this is all going to give us, this is the exact same form as the equation that we had over here. If you compare this to this, it's the same thing, except now M1 and M2 are paired out, or switched out. And so if we, if you don't want to totally redo all of the algebra, it should be fairly easy to just switch out some of these variables. But you should basically find that M1 and M2 are switched in these middle terms here. So we're going to end up with the denominator is the same for all of these, but we have the numerator, these two terms are switched. So this is going to be our expression for A2, again, which we're going to get after just doing a lot of messy algebra here. Now, part E asks for the tension in string A. So this is this equation that I keep copying over, which we had right here, TA. So we have conveniently found this already in terms of everything that we want. We just want to plug in our A3 here. So we would just want to plug this whole expression in for A3 here and simplify. So again, this is going to be pretty messy algebra. So I'm just going to write out the answer here. We're going to end up with G times 4M1, M2, M3, and then the denominator is the same as it is for all these other expressions. And then the next part, part F, is going to ask us for the tension in string F. So if we go back to here, it's string C, and we found before TC has to be 2 times TA. So this is pretty convenient. We can just multiply this whole thing by 2, so we don't have to do out any new algebra. So if I multiply this by 2, this 4 will just become an 8. So this is our answer for part F. And finally, part G asks, what do your expressions give for the special case of M1 equal to M2? So let me write these conditions down. M1 equal to M2 and M3 equal to M1 plus M2. So basically twice the other mass. And is this reasonable? So let's think about if we plug this into any of these acceleration. Here let's just do this on a totally new tab to make this a little clearer. So we have, here's our final expression for A3. Here's our final expression for A1. Here's our final expression for A2. And then these are the conditions that we are considering. So if you plug these in, I'm not going to actually go through and do it, but you can see that you'll find that A1, A2, and A3 are all equal, and they're all going to be equal to 0. So this is going to tell us that none of these are accelerating, and the tensions, so copy over this tension force as well. If we plug these into tension force, we'll find that Tc is equal to 2 times mg. If we say m1 equals m2, we'll define that to be little m. So m3 is 2 times little m. And Ta is going to be m times g. So in this case, the accelerations are all 0. Let's look at what this means here. This tells us that this whole system is in equilibrium. So m1 and m2 are equal, so there's no relative acceleration. The accelerations A1 and A2 are 0. So these two blocks, you can just picture them, they're just going to be hanging and not moving, and that's going to perfectly balance out with m3. So this entire system will just be not moving, and that's exactly what we would expect if these two masses are the same. So this does all make sense and is all consistent.